I'll be presenting a webinar for electromagnetic analysis for brushless permanent motor using Ansys Motor-CAD. So before we go to the demo, I'll introduce you some of the Ansys product that we can provide. So this is all the list of Ansys product that we can provide. So for me, I'm mainly in electronics. So in electronics, there is FHSS. In Ansys Electronics, there's FHSS, Maxwell, SI Wave, iSpec, Motor-CAD, EMA 3D cable, Q3D extractor, EMA 3D charge, and no-head splitter solution. So for today, we are mainly focusing on Ansys Motor-CAD. So what is Ansys Motor-CAD? Okay, slideshow. Okay. So what is an Ansys Motor-CAD? It enables a design engineer to evaluate motor topologies across full torque speed, operating range to optimize their performance, efficiency, and size. Motor-CAD is a template-based design tool for fast multi-physics analysis of electric motors. So these are all the type of electric motors that we can simulate, which is brushless permanent magnet motors, BPM, the brushless permanent magnet auto-rotor motors, the synchronous reluctance machines, switch reluctance motor, synchronous machine, induction machine, single-phase induction machine, permanent magnet DC, and claw pole machines. So inside Ansys Motor-CAD, there are 4 models that we can simulate. So it's an EMAG, electromagnetic. It is for fast template-based electromagnetic performance prediction, mainly for electromagnetic. Then we have a thermal model. Thermal model for thermal performance prediction and advanced cooling system design. And then MEC is for mechanical analysis of stress and displacement in rotor during operation. And finally, the lab is for efficiency mapping and performance across the drive cycle. So for this demonstration, I'll be simulating a BPM motor, brushless permanent magnet motor. So this the GUI, the GUI for the Ansys Motor-CAD. So it's a template based, as I already told you. So inside this geometry, so for radial, you can just plug in the numbers for the parameter. So these are the parameters that we are going to design for the motor. So for the actual parameter here. So after this, I'll go to the software for the demonstration. So this is the actual. So this is the winding pattern. We can set the winding pattern. If you want to lap, concentrate, or custom, the path, yeah, the control upper, lower, or left, right. And we also can set the winding definition. You want the number of strands in these hands, or we can plug in the numbers. So later on, I will show you how. So we can also change the material inside the motor, like this one. You can change it. And then after we set the design, we need to set up the calculation. We set up the drive, the temperature, the performance test. So after we make the design setup, we're going to see the result. So for there are 3 types of result that you can see. First is the analytical result, which is the FEA side of the motor. So you can see the on-load torque, open circuit transient result, the correlating torque, static, OC, open circuit, on load loss result and also the static load. So you can animate the motor and see the changing of the region here. So this is the analytical result. You also can see the numerical result inside the output data. So inside the output data, you have drive, magnetic, phasor diagram, equivalence scale, flux densities, losses, winding, miscellaneous, and all. You can see all the numerical result if you want in numerical. And finally, we also can see the graphical result. So inside this graphical result, you have the currents, terminal voltage, back EMF, torque, correlating torque, gap density, flux density, and flux linkage on load. All of these are in graphical result. So now let's go to the software and let's see how we simulate it. So I'll be opening Motor-CAD. Let me share different screen. Here are the Motor-CAD. So firstly, what we're going to do is you can see my screen, right? The Motor-CAD software. So first, we see the unit first. So inside default, you can see the units. So everything here is in default. If you want to change it, you can change it, but it's preferably to be in default. All the units. So click OK. And then what model that we want to do is magnetic, electromagnetic analysis. And then we change the motor type to BPM. Okay, it's already in BPM. And then we have all these parameter to put in. So if you want to know what is the slot number, what's the slot number, what's slot state eliminate, it already if you hover your mouse at the name here, you can see what it will explain what is a stator lambda is a state elimination outer it's a stator bore diameter. So if you also hover your mouse at the motor, it will show what part is it. Like this one, rotor elimination. This one is the magnet. This one is the copper winding. And this one, the red one is the stator elimination. So it's easy to navigate. So for this parameter, you want to change the slot number 48. Stator and diameter to 198. This one 132. And then 4.1. One is 21 to 13, and this one 27. So if we change here, you can see it doesn't change inside this design right in this motor. So you click on redraw, and it will change all the design according to your parameters. Then we change this one is the stator. Then now we change the rotor. The rotor type is just surface parallel. Okay, wait. For yeah, we use the surface parallel. And what should we? No, we change the rotor type to simple interior V simple. Okay, this one. So you can see it's changed. And then we change it, the pole number to 8. Yes, 1, 6, 17. Yes, no, notch. 8, 0, 1, 6, 17. Magnet with 16. Change this to 1, 150, 2, 2.5. And magnet clearance, we change the shaft diameter to 80 and then change this one to 0 point offset gap out to get in. So we change it to 0.2. Now we click on redraw. So it already changed. And then this on the radial side. Now we see in axial side, we also need to change this. So for this demonstration, we change the shaft still in solid, radial none, and the water length to 260, 160, 150, 80, 150. Then we click on the draw. So they change. Let me check something. 260, 160, 150, should be 150. Okay. And then 18 is supposed to be 18. Control. Okay. Now we can save this. Desktop. Demo. Okay. Okay. And then you can see the 3D design for the motor that we've created. So these are all the full design, so you can hide it to see what's inside the winding. Yeah. So now, after we design this, what we want to do is we see the winding. So if you want to go to winding, just go to this winding tab here and the definition. We see the pattern first. So we want it to be concentric. This one, central 3, 6 turns, and 5, 2, 1. So okay, here so inside this you can see the radial pattern, the linear pattern, the phasor, the harmonics, the MMF, and reflectors. All you can see after you change the parameters here, the pattern here. And next we can see we want to define the windings. So for this one, we want it the coil to be stranded and overlapping. And this one we change the definition to wire size and metric table And for the wire gauge, we change it to 0.885 to 0.8. And we want it to, so this is the diameter, and we want it to be 18 wines, 18 windings here. Now, the number of strands. Now, yeah, we already thank you, draw. We already changed it. Okay. So after that, we want the number. We do not change this. So this one is linear thickness 0.25. Yes. Yes. And conductor separation, we want it to be 0.02. Okay, great. And then, so after we define the windings, we want to change the material. So we go to this input data tab. In the material, we change the stator lamination to N250, N250 35 M, and we change the armature winding. Yeah, it's copper. It's already copper, and we change this rotor lamination back iron to the same as 250 35A. So if you want to know what is this material, you can see inside the material database. Inside this material database, you already have the properties of this material, the thermal conductivity, specific heat density, and you also see the DFE curve, steel losses. So if you want to add your own material, you just click here, add, or you can import it. So yeah, as easy as that. So now we already done the material. Now we go to this calculation tab for to define the analysis setup. So for this calculation, okay, we already set the shaft speed to 3000, and the peak line current definition. So for the peak current, we want it to change it to 480, and then we change this. And then change this. The drive mode is in sine wave, magnetization in parallel, star connection. This one we change it to 65, and the magnet temperature also 65 degree. And what else we change? The DC bus voltage here we change it to 400, and the phase advance we change it to 55 degree. So after, and then we click on this open circuit back EMF and Colvin top, something that we want to observe. And the top here is on load top. Okay. So now after we set up all this simulation, we want to solve it to see the result. So just click on this solve the magnetic model. So it only take a minute and a half, just something like that, to it be simulated. And after that, we can see the result. So this software is very good for rapid prototyping, because we just change the parameter and you can solve it. Change, solve, change, solve. So it's very rapid. So if you inside it R&D or research and development, this is a very good tool for prototyping. So now, yeah, we already solved it. Now we go to this magnetic step to see the result. So inside this result, you can see this one. This is all the file of the result. The coding is the coding top calculation. This one is on the top, the on the transient top for the top calculation, and this one on load loss, the loss calculation from a load transient top. This one is the static OC result. It's for single point no load per result, and this one open circuit transient for open circuit transient result. The open circuit loss calculation from open circuit transient, and finally the static load result. It's a single point on load or static load. So what we want to see first is the on-load torque. You can see it's in flux density. So you can play. If you play this, you can see the animation, the changes of the flux per phase. So it will same goes to all the result. Yeah, you can change the result to which one you want to observe, and then like we this is for the analytical result. So all this you can observe it, and then for the numerical result, you can just click on this output data. So you can see all the numerical result here, all the value and its units. So you can observe the DC bus voltage, the line, all this numerical of this drive, the value of the numerical in the drive. In the magnetics, you can see the torque, all the power on this. And we also can observe the phasor diagram, the back EMF is resistor, all this. And the equivalent circuit, also the flux densities. You can see the air gap, stator, the losses. You can see the amateur DC copper losses here, total losses on load. Yeah, you can observe all this numerically. The winding, miscellaneous, and the material. So after we see all this, you might want to see the graphical result. You want to observe it. So inside this summary, you can compare and contrast between graphs. So you can select which graph you want to add or remove here. And if you want to observe it individually, you just go to the current tab, terminal voltage, back EMF, torque, recording torque, the air gap, flux densities, flux linkage, and all this. Yeah. So that is for the simulation. So for this demonstration today, I only show you the how we do the electromagnetic analysis, and maybe for our next webinar, we focus on terminal or lab or mechanical. So yeah, you can suggest me which which part of the module you want after this for the next webinar, or you can see which others motor. Yeah, if you want, if you want to. So that's it for today's webinar for electromagnetic analysis for BPM motor. So thank you all for joining. I want to give the screen to Zuleika for the next phase of this webinar. Zuleika, you can take the screen.
Thank you, Mr. Farhan, for this informative webinar on Ansys Motor-CAD. I hope you have been enjoying the presentation so far. I already launched a poll. Please select the appropriate response and click submit. Now, it's time to address your question. Feel free to type your question in the chat features, which you will find at the right of your screen. We will do our best to answer as many questions as possible during this session. So, does anyone have question regarding this topic? While we are waiting for question to come in, I would like to remind our participant that sometimes it takes a moment for a question to be formulated. Do not hesitate to ask about anything related to our discussion today. So anyone has question regarding this topic? Because we have time to answer the question. It seems that we might not have any question, but that's perfectly all right. Sometimes topic can be quite comprehensive and may not lead to immediate queries. Rest assured, if you do have question later, you can always reach out to us via email. For Mr. Farhan's email, you can see on the screen, or our training center, or also on social media channel. Mr. Farhan, is there anything else you wanted to cover?
Probably there are some of question people might ask, like what's the difference if you simulate in Ansys Maxwell instead of using the Motor-CAD, right? So the difference is if you simulate a motor in Ansys Maxwell, it got more accuracy than Ansys Motor-CAD, but it's hard to simulate in Maxwell. It's like you can't rapid prototyping because it's not a template based. Instead, in AutoCAD, it's a template based for motor design. So you get the accuracy versus the prototype, the designing. So Yeah, I think that's all that I want to share. Thank you all for attending and joining this webinar. So if you have further question, you can just email me. So yeah, that's it for today.
Great. Thank you, everyone. We appreciate you being here. We also encourage you to connect with us on social media to get the latest information. If you have additional question, you may contact us by email or telephone. We are happy to provide additional support. That's all. Thank you all for attending. We hope you have learned and enjoyed this presentation. Have a nice day.